So in Unit 2, Lesson 2, we're going to learn some more derivative rules and explore the derivative as a rate of change. So I'm going to really strongly recommend that maybe we start making some flashcards because we're going to want to memorize a lot of these rules because we definitely don't want to use the definition of the derivative every time. So at the top of page 14, the first thing we're going to talk about are rules of basic transcendental functions. So a transcendental function is like a function involving like exponentials or trigonometric functions or logarithmic functions. So we have like our basic polynomial functions, and then we also have what we call transcendental functions. So these first four rules, we're going to learn that the derivative of the sine of x is the cosine of x. The derivative of cosine of x is negative sine of x. So we're definitely going to want to memorize those. The derivative of e to the x is just e to the x. And the derivative of the natural log of x is 1 over x. So if we just kind of explore this, if I think about the function cosine of x, if I remember that I could think of the derivative as being the slope of the tangent line, I'm going to write tan line, but I mean tangent line. So if I kind of zoom in to the cosine of x, that's as far as I can zoom. If I start where x is 0, if I think about where this graph we said is like locally linear, I'm going to see that right there at the top, a tangent line right there would be horizontal. So it would have a slope of 0. So I know on the graph of f prime, I'm going to start right here at 0. And then as I look, maybe let's estimate where about pi over 4 would be. I see that this slope here is like negative, that we've got some negative slopes, but they first get more negative, right? Because we're coming from 0. We have some tangent lines that would have a negative slope. And then at pi over 2, we're going to have a very negative slope there. But as we continue to where x is pi, we're going to have another slope of 0 at pi. So it's like our slopes are getting more negative, like steeper and steeper and steeper. And then they start to get less negative again until we get to where we have a slope of 0 again. So if I think about that, at pi over 2, that's where my slope is going to be the most negative. And it's going to kind of look like this. All right, so then from pi to 3 pi over 2, our slopes are slightly positive, and then they get steeper and steeper and steeper. After 3 pi over 2, our slope of our tangent line would get a little less steep until we hit 2 pi, where it's 0 again. So we said our slope is going to be the greatest at 3 pi over 2. So if we kind of sketch this graph of what the slope of our tangent line looks like, well, this is a reflection of the slope of sine of x. So this is like -1 times the sine of x. We could also do the same thing thinking about e of x. So for example, I know out here to the left, e is never totally horizontal. This slope is really close to 0, but it's not actually 0. And I could see, like, as I draw in these different little pieces of slopes of our tangent line where we're locally linear, I could see that my slope gets steeper and steeper and steeper. So again, it's like my slope is never actually 0, but it's close to 0. And then it starts to get steeper and steeper and steeper and steeper. So it turns out that the derivative of e to the x is actually just e to the x. That e to the x models the slope at any particular input of the actual function e to the x. So below, we can actually prove that the derivative of sine of x is equal to cosine of x. And again, I think when we look at this proof, you're going to understand why we really want to memorize these rules of our basic derivative rules. So if I were to write the derivative of the sine of x using the definition of the derivative, I could write that as the limit as h approaches 0 of the sine of x plus h minus the sine of x, all of that over h. And right now, if I were to plug in a 0 for h, my numerator would be sine of x minus sine of x, which is 0 over 0. So I know that I have a whole. So I need to be able to do some type of manipulation to eliminate that hole. And this doesn't look like anything we've seen yet. So I'm going to use a property that we learned prior to this class, that when I have a sign of a sum, so like let's say I have the sign of a plus b, I could think of that as the sine of the first term of my sum, so like the sine of a, times the cosine of b plus the cosine of the first thing, so the cosine of a times the sine of b. So you would have learned that in Honors Algebra 2 or Honors College Trig. So if I use that to rewrite my numerator, I could now rewrite this as the limit as h approaches 0 of the sine of x times the cosine of h plus the cosine of x times the sine of h. And again, when I did that rewrite just now, all that is this first term in our numerator, the sine of x plus h. So we still have to subtract the sine of x from that. And again, this limit is all over h. All right, so as we are working through this, we know that we can do some things with limits, like we can use some properties to rewrite them. And we can also, we know that like when we have addition, that is commutative. So I'm going to just kind of reorder what's going on in our numerator here. And I'm going to go ahead and think of this as the limit as h goes to 0 or h approaches 0. And I'm actually going to start with this middle term. So I'm going to start with this piece, the cosine of x times the sine of h over h. And I'm going to peel that off to be the cosine of x times the sine of h. And I'm going to give that its own denominator there. And then I'm going to add to that all the other junk. So we've got the sine of x times the cosine of h, that was our first term in our numerator, minus the sine of x, that was our third term. So all we've done so far is just kind of reorder the addition in our numerator and kind of giving those two things their own denominator there. All right, and now we could rewrite this again. I could think of this as the limit as h approaches 0 of, so in my first term over here, I'm going to peel off the cosine of x piece. And I'm going to think of this as the cosine of x times the sine of h over h. Sorry, I know my n's and h's kind of look the same. And then separately, I'm going to add to that. We could factor out of like this second term. I could think of this as factoring out a sine of x factor, so that my numerator would then be the cosine of h minus 1. So my second term, I could pull out my factor of sine of x and multiply that with the cosine of h minus 1, and again, all of that over h. So we just kind of did a little reorganizing there. And then lastly, and there's like a reason that I'm manipulating it this way, I could also factor out a -1 here. So if I were to factor out a -1 for my numerator, I could rewrite the terms of my numerator. So this becomes the limit as h approaches 0 of cosine of x times the sine of h over h. So I haven't changed anything yet about this first term. But when we pull out a -1, I'm going to pull it out front and write this as subtraction. So now we have the sine of x, and because we're factoring out a -1, this becomes 1 minus the cosine of h over h. And you might notice I'm trying to manipulate this to look like our particular rules that we learned for dealing with limits when we have a hole, and we had some specific trig limits that we learned in Unit 1. All right, so now we could think about this, really, I could break this into two different limits. I could think of this as the limit as h approaches 0 of the cosine of x times the sine of h over h minus the limit because remember, a limit of a difference is a difference of limits. So minus the limit as h approaches 0 of the sine of x times 1 minus the cosine of h, all of that over h. All right, so now we really could break this into like multiplication as well. Like we could write this differently, or I could just think about this. I know that when I go to plug in my zeros now, that like if I look at this first limit right here, that when I plug in a 0, that when I get sine of 0 over 0, so the limit of just this piece of sine of h, that is just going to become 1. So really, I could think of this first limit as being the limit as h approaches 0 of the cosine of x times 1. And then if I remember my other trig rule, that when I have the limit of 1 minus cosine of some junk over the same junk, that's going to become a 0. And again, these were the two trig limits that we learned in Unit 1. So this becomes effectively the limit as h approaches 0 of the cosine of x times 1 minus the limit as h approaches 0 of the sine of x times 0. And so the sine of x times 0 is just 0. So all of that to say, the limit of cosine of x as h approaches 0 is just cosine of x. So do we really want to have to do that much work? No, we absolutely don't. So all that to say, we want to memorize these basic derivative rules here. Okay, we also have a rule for a sum and a difference. So similar to working with limits, we know that the limit of a sum is a sum of limits, or the difference of a sum is a difference of limits. Well, we can apply the same idea to derivatives, that if I have the derivative of a sum or a difference, so either f plus g or f minus g, that's going to become the derivative of f plus or minus, depending which sign I used on the first part. So the derivative of f plus or minus the derivative of g. So much like limits, a derivative of a sum or difference becomes a sum or difference of the derivatives. So let's look at these examples, and these are pretty straightforward. So if I'm asked to find the second derivative for y, well, we always have to start at our first derivative. So if y is 4x squared plus 2x to the fifth, when I find y prime, I know using the power rule that I'm going to take my exponent 2, and I'm going to multiply it with that constant out front. So I'm going to get an 8x to the first power here, because I'm going to subtract 1 from my exponent. And then I can add to that my second term. So the derivative of my second term, 2x to the fifth, I'm going to take my exponent 5, I'm going to multiply it with the 2 out front, so that's going to become 10. But then when I write my new exponent, I have to subtract 1, so 10x to the fourth. All right, so that's our first derivative. When we find our second derivative, we're taking the derivative of our first derivative. So 8 times x, again, I could think of that as 8x to the first power, that 1's going to multiply with the 8, and we still just have an 8. And then I get like x to the power of 0. But x to the power of 0 is just 1. So 8 times x to the power of 0 is just 8. And so when I do this multiplication, I'm going to multiply my exponent 4 with the 10. So I get 40 x to the third power, because using the power rule, I'm going to subtract 1 from my exponent. And I normally wouldn't write the x to the power of 0 part. So this just becomes 8 plus 40x cubed. So as I think about this, when I take the derivative of a piece that is linear, so like 8x is linear, I'm always just going to get its coefficient as my derivative. If I take the derivative of something that is a fourth degree polynomial, like 10x to the fourth, I know that my derivative is going to be a third degree polynomial. So when we're working with the power rule, or we're thinking about polynomials, it's easier because like if I take the derivative of something quadratic, it's going to be something linear. All right, the next example, we're asked to find y prime for y equals 3x to the fourth minus 2 root x. And remember, we don't have a rule for radicals, but we do have a rule for dealing with powers. So I'm going to first just rewrite this as y equals 3x to the fourth minus 2 times x to the 1/2 power. So writing that with a rational exponent allows us to use the power rule there. So now when we take our derivative, y prime, when I use the power rule on 3x to the fourth, we know the 4 comes out, multiplies with the 3 to make a coefficient of 12. And we now have x cubed instead of x to the fourth power. And for the second term, the 1/2 comes out and multiplies with the 2 or the -2, depending how you're thinking about that. So we get a -1. And we just have to be real careful when we subtract 1 from our exponent. 1/2 minus 1 is -1/2. Now, in math, we generally try to clean up when we have a negative exponent. And on a multiple choice test, there's sort of a standard format that the College Board, that AP kind of expects us to use. So we're going to get rid of a negative exponent. So when I do that, I want to point out that we have two terms here. This is a term and this is a term. And only one of my terms has a negative exponent. So when I rewrite this, I'm going to first start with leaving 12x cubed alone. But I'm going to think of this as like -1 over x to the positive 1/2 power. And that's the same as saying -1 over the square root of x. So I might do that in my next rewrite and say this is 12x cubed. I should put a y prime out there. -1 over the square root of x. And so here's the other thing that AP will often want us to do is we will often need to get common denominators. You'll notice on a multiple choice test that this is probably not how the answer would be written, even though this is this is our derivative. This is correct. So if I think about how I can kind of clean this up, I need to get common denominators. So that means I need to multiply by the square root of x here and on top. And I'm going to write this two different ways. Remember, the square root of x is equal to x to the 1/2 power. I realize one of those I wrote as a power, one I wrote as a radical. If you can flex in between them, or you could write them the same way at first. But now we have a common denominator of the square root of x. So when we go to rewrite this, all we want to do now is just clean up this piece in our numerator. So when I multiply two powers of the same base, I add their exponents. So 3 plus 1/2, we would probably just write that as 7/2. So 6/2 plus 1/2. And then I still have -1 in my numerator, and this is all over the square root of x. So another thing that AP is funny about is that when we have a radical, or when we have a power with like a rational exponent, if it's 1/2 or if it's -1/2, we will often go back and rewrite that with the square root. So we would write x to the 1/2 power as the square root of x. However, if your exponent is anything else, like 1/3 or 7/2, we're just going to leave that as a rational exponent. That is how we tend to see these things when we are working with AP. All right, on the next page, we're going to talk about, we're not going to do that yet on the next page. On the next page, we are going to just do a couple more practice problems. So I would encourage you to pause the video and work these out for yourself and then check. Okay, I'm going to assume that you did that. So for the top example, we're asked to find g prime, and we're given the function g of t is 2 times e to the power of t minus 5 times the natural log of t. So again, we need to use our basic derivatives for these basic exponential and logarithmic functions. So if I'm finding g prime of x, well, I know that, or sorry, not g prime of x, g prime of t, I know that 2e to the t, well, 2 is just a constant multiple, and the derivative of e to the t is just e to the t. So the derivative of that term is just 2e to the t. And then same when I get to the minus 5 ln of t, 5 is a constant multiple. The derivative of ln of t is 1 over t. So I could just rewrite this as 2e to the t minus 5 over t. And who knows, maybe our answer would be written that way. So again, whenever we're taking a multiple choice part of a test, and a lot of our basic derivative rules will be assessed as multiple choice style questions, because if it's a free response question, you could absolutely leave your derivative in the first way I wrote it. Like you don't have to change anything. But if I'm trying to find my answer in a multiple choice style test, often we might be looking for common denominators. So if I need to make both of my terms have the same denominator, in this case, the denominator is t, I would need to multiply by t over t for my first term. So the last way we might see this written would be 2t, we usually put the t first, e to the t minus 5, all of that over t. So either of these are fine. Like the first way I wrote that derivative without the orange t's, or the second way where we got common denominators. So again, on a multiple choice test, it's just like, can I make my answer match one of the answer choices? All right, in this other example, we're finding the second derivative of f, and again, we're given f of t. And we want to be really careful when we're working with sine and cosine about sign changes, and by that I mean SIGN, like positive versus negative. So when we find our first derivative, I know I have 3 as a constant multiple. It just kind of comes along for the ride. And the derivative of the sine of t is the cosine of t. There's not a sign change, SIGN sign change. But I have to be careful when I get to my second term. I have 2 as a constant multiple, but the derivative of cosine is negative sine, or the opposite SIGN sign that cosine had. So when we write this derivative, we're going to get that our first derivative, f prime of t, is 3 times the cosine of t minus 2 sine of t. So that negative 1 factor in front of sine of t, we're just going to pull that out and multiply that with the 2. But we're asked to find the second derivative. So now when I take my derivative of f prime of t, I have to watch out again here that I get 3 times negative sine of t. So anytime I take the derivative of cosine, in fact, more generally, any cofunction, I'm going to have a negative derivative. And then over here, my negative 2 comes along for the ride. The derivative of sine of t is just positive cosine of t. So I could rewrite this as negative 3 sine of t minus 2 cosine of t. So we just really want to be careful with sine and cosine, which derivative has a sign change, which gives us a negative derivative.